Okay, so before we start today, does anyone have any questions for me? All right, good. So last class, we finished off by looking at this very simple piece of code for finding the maximum value in an array. And we analyzed what that code does, how many times the maximum value is updated if the array is a random permutation of n distinct values. And we saw that the answer was this, the expected number of times that this update of the maximum happens was this sum I equals 1 to n of 1 over I. To write it out longhand, it's 1 plus a half plus a third plus a quarter and so on, all the way up to 1 over n. And I said that that's so important that we give it a name, Hn. It's called the nth harmonic number. And it shows up all the time in probability and randomized algorithms, in the analysis of randomized algorithms. So it's useful to know some things about it. And I told you that basically this thing is very close to ln of n, the natural logarithm of n. Okay? So one fact that you need to remember or recall from calculus is this. So if you take the integral from 1 through n of 1 divided by x with respect to x, that thing is the natural logarithm of n. Okay? So you can dig up an old calculus textbook and look that up. It's one of the sort of the common integrals that you learn about. And with different constants here, you can get logarithms, different logarithms on the side with different bases, but the natural one, where it's just 1 over x, you get the natural logarithm of n. Okay, so that's one thing you should remember. Now, let's look at this sum and think about it geometrically. So here's a picture that's supposed to represent this sum. So these things are a bunch of rectangles. It's not to scale, so the y scale is different from the x scale. But for example, the first term in this sum is 1, which if we want to represent it as a rectangle, it's a rectangle of width 1 and height 1. Okay. So if I take the area of that rectangle, I get the first term in this sum. Second term is a half, which here is represented as a rectangle of width 1 and height 1/2. So the area of that thing is a half. So this is the 1, this is the half. And similarly, the third one is width 1 and height 1/3. So this is a third, a quarter, and so on, all the way up to this tiny little sliver one here, which is width 1 and height 1 over n. Okay. So that sum is exactly the area of all these rectangles. You agree? Okay. Now, this integral, so this is an integral of a function, and the function is f of x is 1 over x. So if we draw, then it goes from 1 to n. So if we draw that function, 1 over 1 is 1, and 1 over 2 is a half. So there's another point on that function. And 1 over 3 is a third, and 1 over 4. So these are all points on this function, including even here up to 1 over n. And the function is somehow smooth in between those. Okay. So this thing is the function f of x equals 1 over x. So in this picture then, what is this integral? So one of the sort of basic lessons in calculus is you can interpret an integral as, as the signed area under the curve. In this case, the curve is always positive. So that integral is actually giving us all of this area here. Right? So this brown stuff in here, this is actually the integral from 1 to n of 1 over x with respect to x. So notice that that area contains this rectangle and this rectangle and this rectangle and this rectangle and so on. So this area contains all of these rectangles. And then if I just tack on a little more, another rectangle here, it'll contain everything. So what does that mean? Well, that means that h of n is contained in this thing plus the area under this curve, that's this integral, but this integral evaluates to ln n. So this tells us that h of n is smaller than 1 plus ln of n. Now, on the other side, if I just take this curve and move it over by 1 unit, then instead of passing through the right tops of these things, it passes through the left tops. So it goes like this. And so on all the way to there. And so moving it over to the left like this doesn't change the area underneath it. It's still exactly the same area underneath it. But notice now that, well, this area, this part here, well, it's contained in this first rectangle. So the area of this thing is smaller than the area of the first rectangle. And this part is contained in the second rectangle. So the area of this thing is smaller than the area of the second rectangle. This one is contained here, so it's smaller than the area of the third rectangle. And so actually the area under this curve then is contained in all of these rectangles, which means that it must be smaller than all these rectangles. But the area under this curve is still that integral, which is evaluates to the natural logarithm of n. Okay. So this thing is sandwiched between natural logarithm of n and 1 plus the natural logarithm of n. And so once you see one of these harmonic numbers in your head, we kind of associate that with, that's roughly the natural logarithm of n. And usually for what we're studying in computer science, that's a good enough estimate for us. Now this technique, how did we sandwich this thing, this weird looking sum between two nice formulas? So what we used here is a more general technique, which is called bounding a sum by integrals. You'll maybe learn about it a little bit more in a future course. But typically when you have a sum like this, where all the terms are always getting smaller or always getting bigger, then usually you can take whatever this function is and take the integral instead. Okay? And if there's various rules depending on whether the function is always getting bigger or always getting smaller, but then you can always sandwich the thing between two of these integrals like this. All right. So questions there? Good. All right. So let's just keep that. Let's save that over here. just so we remember it for the rest of the class. It's going to come up a couple more times. All right, so this is the first and only class in which I've brought a computer with me. And that's because today we're going to study a really important algorithm. It's really important because it's practically important. So it's an algorithm that is used all the time in practice, and it's fast in practice. But it's also important because it was one of the first algorithms that relied on randomization to be fast. And not just fast, but fast and simple. So it's called the quicksort algorithm. And here's how it works. I'll write down some code. So quicksort takes as input an array and two indices, I and j, into that array. And it's supposed to sort the subarray ai plus 1 up to aj. Okay. So this is assuming I is less than or equal to j. It should do that. But in fact, it's going to check that first. So there's only work to do if indeed I is less than j, right? Because if I equals j, that means it's asking me to sort a subarray of length 1, and a subarray of length 1 is already sorted. And if and so what it does is it picks an element p to be a random element in ai up to aj. So from the subarray that it's supposed to sort, it picks a random value and saves that, calls it p, and then it calls a function called partition that takes all the same arguments plus p. And what partition does, so I'll just draw the effect of partition. So I have the array A, I have an I, and I have a J. And so there's a bunch of stuff in here, AI up to AJ. How many items are in here? J minus I plus 1. It's good to remember that. And yeah, so it takes all of that plus this value p, and it rearranges the array so that what you get, so this is here, this is here, is partial sorting. So you get p somewhere in this thing, actually at position k, and it's going to return that value k. And before that is only stuff that is smaller than p, and after that is only stuff that is bigger than p. And that's assuming that all of the values are distinct so that you don't have any equal values. If you don't like that, then everything less than or equal to p, then everything before p. Okay. So that's what partition does. All right. And it returns the value k, and the value k is this index of where p ended up after doing this partition. And there's different implementations of this partition function, but there are nice, clever ones that all they do is maintaining a couple of pointers, scan through here, compare each value with p, and just by carefully deciding what to do depending on the comparison, in one scan through this thing, they organize it this way. And everybody is compared to p exactly once. And nothing else needs to be compared with other things. So all this is comparisons with p. Okay, so that's what partition does. And so here we pick this random element, we partition, so that now the array looks like this. And then we quicksort the first part, so that's A, starting at position I and going up to position k minus 1. So we recursively sort the first part. And then we recursively sort the second part, which starts at position k plus 1 and goes up to position j. So that's this part starting at k plus 1 all the way up to j. And once we do that, then the whole array, the whole subarray is sorted because, well, by, let's say, induction, this is sorted and all these values are smaller than p. Then comes p, and then this is sorted and all these values are bigger than p. So that's sorted. It's a really simple algorithm. If you don't care about being too fancy with this partition function, then there's the code for it right there in Python. Right? So if the length is less than or equal to 1, we don't do anything. We just return the input. Otherwise, we make a random choice from the input. And then we split into the stuff smaller than p, the stuff that's equal to p, and the stuff that's bigger than p. And we have to quicksort the first part and quicksort that last part. And that'll return a sorted version of A. Not the most efficient implementation. In fact, the most efficient implementations sort in place, so you don't need to create additional arrays. You do everything inside of A, but this is certainly a simple, clean implementation. So let's think about this algorithm and whether it's going to be fast or slow. Presumably the name, it's not called quicksort because it's slow, but we can't be sure. And we've already seen a sorting function before. There it is, insertion sort. It's the one we analyzed last class. And for insertion sort, we kind of looked at the number of comparisons it does. There was a particular line in the code that was the problematic one, the one that might execute many, many times. And that line was doing a comparison or a swap. Both are executed about the same number of times. And we saw that, well, insertion sort, in the best case, you give it a sorted array, and then insertion sort, all it's basically doing is checking that it's sorted. So it goes through the array indices one at a time and checks that the element I is larger than the element at position I minus 1, the element that just comes before it. And if the array is already sorted, that's all it has to do. So then it does something like n minus 1 comparisons. But then we saw actually there's a bad case where the array is sorted in reverse order. And when that happens, then everything has to be compared with everything else. So it basically has to reverse the array, and it does this with swaps, which means that every pair of elements is in the wrong order, so they get swapped, and before they get swapped, they get compared, so that there you get actually n choose 2 comparisons on an array of length n. And the interesting thing for this class was the average case, and this was for insertion sort. That was when we assumed that the input array is a random permutation of n elements, and we saw that that's n choose 2 divided by 2 was the number of swaps that are done, and if you translate that to comparisons, there's actually an additional n comparisons, the ones that don't result in a swap, the ones where you stop. Okay. So best case was something like n, worst case was n choose 2, and average case is about n choose 2 divided by 2. So we can ask the same kinds of questions about quicksort. Let's start here with quicksort. What's the worst thing that can happen with quicksort? So let's, I don't know, take some input array. Maybe this one. And so, and I should maybe specify, so this was insertion sort, sorting an array of length n, and here this is quicksort, sorting an array from the first position all the way to the nth position. So I call quicksort with, this is I, and this is j. So yeah, I is less than j. Pick a random element. So what would be sort of a bad element to pick in this case? Yeah? Yeah. So if I pick the smallest value, for example, if I pick 1 here, then what happens when I partition? Well, when I partition, everybody gets compared to 1. No, shouldn't have had 2 twice there. Let's put 3 there. Everybody gets compared to 1, and it gets split into 2 parts. The stuff that's smaller than 1, but nothing is smaller than 1 itself, and then all the stuff that's bigger than 1, and that's this part here. Okay. And then I recursively sort the first part, and nothing happens because the first part is empty. But I still have to recursively sort the second part. So now I recurse with this being the position of I, and this thing here being the position of j. So I've already done n minus 1 comparisons. Everybody was compared to 1, and now I have to continue here. So what's the worst thing that can happen now?
Choose 2 and then...
Yeah. So now if I choose 2, I'm in trouble again because partition is going to compare everything to 2, and actually it's not even going to change anything. The only sort of progress we've made is now we don't have to recurse on the stuff that's smaller than 2 because there is none, but we have to recurse on the stuff that's bigger than 2, so we have to recurse on this thing. And now I can make a bad choice, and I could pick 3, in which case after partitioning I get 1, 2, 3, 5, 7, 6. And another bad choice now would be 5, which gives me 1, 2, 3, 5, 7, 6. And then now it finally doesn't matter. If I pick 6 or 7, it's going to give me the same result, but only then do I finally get a sorted array. Okay. And this is bad because what happened here is, well, to get from here to here, I had to compare everything to 1 just to get this first step done. So that was already n minus 1 comparisons to go from here to here. And now from here to there, everything except 1 was compared to 2. So that's n minus 2 comparisons. And from here to here, everything except 1 and 2 was compared to 3. That's n minus 3 comparisons. Well, if you sum all of that up, you get n times n minus 1 over 2, either using Gauss's formula or by realizing that, oh, actually everything is compared to everything here. Each of the n choose 2 possible comparisons actually happens. So everything, to see that, any element will be compared to all the elements that are smaller than it. So that's bad. Worst case number of comparisons is n choose 2. Any idea about the best case?
Choose just the middle.
Yeah. So it seems like picking the smallest thing as the pivot is bad because it leads to this n choose 2 comparisons. By the same line of reasoning, picking the largest one every time is bad. So something we might hope for is, well, actually, maybe we get really lucky, and every time we pick the value whose rank is in the middle, so that's called the median value, and we end up with P is there, and you get something like n minus 1 over 2 over on this side, and n minus 1 over 2 over on this side. And then you recurse on each side, so then, this gives you 2 things which split again evenly, so this is this is about n over 4, about n over 4, and same thing happens when you recurse on these sides, about n over 4, about n over 4. So have we seen an algorithm that has this structure before? Merge sort did that, right? So merge sort, it was a different algorithm, but in terms of the kind of work it does is it takes an array, it splits it into 2 equal parts like this, recursively sorts, and then it has to do about n comparisons. And this is doing this similar thing, right? So this is doing n minus 1 comparisons to split into 2 equal parts, and then it doesn't have to do any comparisons later, but it already did them. So if we analyze this process carefully, we'll get the same answer we got for merge sort. Okay. So roughly, that's n log base 2 of n. Okay. So n log base 2 of n is nice. I mean, it's better than n choose 2 or n squared. On the other hand, this is just what happens in the best case. And in fact, if you look at insertion sort, in the best case, insertion sort does better than this. In the worst case, the 2 do the same. So the interesting question is, well, what's going to happen now in the average case? So, and in this case, for quicksort, average means average over these choices of P. So the expected number of comparisons. All right, and it doesn't look very hopeful because here we ended up about, basically the average was half of the worst case. If quicksort's going to do that, then it's not much better than, in fact, it's not any better than insertion sort. So let's see if quicksort is actually any better. So here's the 2 implementations of those things. This will just run them. So let's sort 2 arrays of length 100. Okay, so both of those seem to happen more or less instantaneously. Let's do 2 arrays of length 1,000. I don't know. Did you see any difference there? do two arrays of length 10,000. Quicksort was done instantly, but insertion sort still chugging away. Finally, it's done. Let's try 100,000. So quicksort took maybe a second there, and insertion sort is still going. And whatever time it took to do 10,000, it's going to take about 100 times more than that to do 100,000. So that'll be going for a little while. Maybe I'll leave it on while we continue, but we're not going to wait for it to finish. If anyone spots it finished, anyone sees it finished, that's great. Okay, so looks like the answer for the average case is going to be quite different. To me, it looks like quicksort is running a lot faster. So the hope, and in fact what we'll see, is whereas insertion sort, the average case is about the worst case, for quicksort, the average case is about the best case. So it's almost like the best possible thing happening. All right, so how should we proceed from here? Well, we're trying to count something very specific. So let's make sure we've defined everything really carefully. So let's say x is equal to the number of comparisons done by quicksort. And we'll assume A contains n distinct values. And let's just say actually the values are the integers 1 through n. Okay. Just so we have names for those values. All right. So notice I just said A contains these distinct values. I didn't say that it's a random permutation of those values or assume anything about the order that they appear in, just that they're all different. So unlike insertion sort, there's no, the randomization in quicksort happens in the algorithm, it's not in the input. All right. So last class we were looking at the main technique. So this looks complicated, right? Number of comparisons done by quicksort. Quicksort is a recursive algorithm. And this looks tough, right? This comparisons happen when we do this partitioning, but there's all kinds of recursion going on and so on. So this looks like a complicated random variable. So what do we do with complicated random variables? Wait, what? Break it down, and break it down into the most simple things possible. And simplest kinds of random variables are indicator random variables. And we usually try and read the plain language definition of the variable we're studying. And whenever we see the number of is the way that this thing is defined, then usually the next thing tells us exactly what we need to study as our how we want to break it down. What are the pieces? So let's say for little x less than y, where x and y are in our input array, define the indicator ixy, which is equal to 1 if x is compared to y and 0 otherwise. And So the X talks about the number of comparisons done by quicksort, and this one looks for every X and Y in our input array. We have an indicator that tells us whether or not those two things were compared. So that means that X will be equal to the sum over all x's less than y. We saw how to enumerate those. X counts from 1 to n minus 1. Y counts from x plus 1 up to n of I x y. The only thing we should check is that we never compare the same two things twice. So this will be true, this is true, as long as we never compare x and y more than once. And we can check that because when do we compare x and y? Well, the only comparisons happen during this partitioning algorithm, and the only comparisons that happen are we compare everything to the pivot p. So we'll only compare x and y if x is the pivot or y is the pivot, and the other one, y or x, happens to be in the array that we're considering, the subarray that we're considering. And once we've placed p, so that means we've placed x or y, we're never going to do any more comparisons with this. It's already sitting in its final location. Yeah? What's above it? N minus 1. So x equals 1 to n minus 1, y equals x plus 1 to n. So that's our recipe for enumerating all pairs x and y with x less than y. Okay. And indeed, so this is valid because if x and y are compared, they're never compared again. So then all we have to do is to count the number of comparisons is count the number of pairs x and y that are compared. And if this is true, that means that the expected value of x is equal to the expected value of this sum. What is the next step? Hopefully you haven't forgotten already. Yeah. The expected value of the sum is equal to the sum of the expected values. So that just means we bring this thing inside. Okay. So now we need to know this expected value. This is an indicator random variable. So what is it that we really need to know? Yep.
Probability that x is equal to
The probability that the random variable is equal to 1, which is the probability that x gets compared to y. Okay. All right. So that now is not as trivial as we've seen in the past. Now we have to really understand how this algorithm works. And maybe it will be helpful to have an example. So let's run quicksort on this really quickly. We'll pick a first value p, and let's say 5 will be our first pivot. So then we'll partition this array into two parts, 2, 1, 3, 5, 7, 6, 8. So that guy's fixed. Then we recurse on this part, and maybe we pick 1 as our pivot. So then this part gets split into 1, 2, 3. 5 is there now. 1 is already where it's supposed to be. This still has to elements in it, so we pick a pivot and partition. So we'll take maybe 2 in this case, and that then fixes everything. 1, 2, 3 is fixed. There's 5 still fixed. And now we're done sorting the first half of this thing. We come back up and we still have to sort the second half. So let's pick a pivot. In this case, let's take 8. So take that as our pivot, and that'll give us 7, 6, 8. Nothing changes. And now we need to pick a pivot out of, we still have this to sort, so we pick a pivot at 6, doesn't matter now. And when we do that partition, so the recursive structure looks like this, right? This is where the first split happens. Next time, this is where the second split happens. Over here, this split, and here is not so exciting. So that's the stuff that happens in this algorithm. Okay. So let's pick a particular x and y. So let's say x equals 3, y equals 8. So in the execution of this algorithm, did 8 and 3 ever get compared? So someone say yes or no and explain why not. Yeah, or why.
Because it was never, like, either 8 or 3 were chosen as p.
Yeah. So what happened in this execution is the first pivot was 7. Everything got compared to 7. 3 got compared to 7, and 8 got compared to 7. And so what happened when we picked that 7 is 3 went off to the left, and 8 went off to the right. And now they'll never be compared because they're never in the same problem again. Yeah? Oh, sorry, 5. I don't know why. Yeah. We picked 5. Good. Everything else I said is still true. We picked 5. 3 was smaller than 5, so it went off to the part that's smaller than 5. And we picked, and 8 is bigger than 5, so it went off to the part that's bigger than 5. So we never compared those two things. Okay. Good. All right. What about What about 8 and 7? So x equals 7, y equals 8. So they were compared, and they were compared from going from here to here. Because here we selected 8 as the pivot. We were working on this set that has 7, 6, and 8 in it. And once you pick something as the pivot, everything gets compared to it. So in particular, this is where we did this comparison and determined that 7 is less than 8 in going from here to here. All right. So notice a couple of things. Something happened before that, which was before that we picked 5 as a pivot. And that didn't cause us to compare 7 and 8. But all it did was shove 7 and 8 into the same sides, because both of them are bigger than 5. They both went off to the same side, so we didn't know yet whether, at this point, we didn't know yet whether 7 and 8 were going to be compared. All right, so let's think about whether we can, is that insertion sort done? Oh, good, insertion sort done. Yeah, finished. Let's try it on an array of length 1,000,000, see if that finishes before the end of class. All right. This is boring anyway. We know what's coming. Okay, so let's say, when does quicksort compare X and Y? So, look at the set X, X plus 1, X plus 2, all the way up to Y. Okay. At some point, X picks X. Quicksort picks a pivot, and let's give this set a name. I don't know. R for range. So it picks a pivot in R, right? I mean, eventually, this range is of length bigger than 2, or bigger than or equal to 2. And so quicksort always picks a pivot if the length of the range is bigger than or equal to 2. So at some point, there's a first time when quicksort picks a pivot that's in this set. And when it does that, so it maybe was working on some subarray, some subproblem that contained both X and Y. That means it also contained everything in between them, and maybe it even contained more stuff. Some stuff bigger than Y and some stuff smaller than X. But at some point it picks a pivot that's one of these things. Now, at that point, the pivot that it picked, I mean, it's a random choice, so it's equally likely to be any of these, right? Okay. So that's the first thing, is whatever that first one is that quicksort picks in this set is equally likely to be any one of these things. Now, so pivot P in R. So what are the things that can happen? If P is equal to X, so it picks this as the pivot, then X will be compared to Y, right? This is the pivot, and we partition around X, which means everything is compared to X, which means Y is compared to X. So if P is X, then X gets compared to Y. Similarly, if we pick the pivot, the first pivot that we pick from this set is Y, then everything in this set gets compared to Y, including X. But otherwise, if I pick, for example, X plus 2, then what happens is everything in this set gets compared to X plus 2. We get a collection of stuff that's smaller than X plus 2 that includes X. And we get a collection of stuff that's bigger than X plus 2 that includes Y. And now X and Y are in two different subproblems. They'll never be compared. Okay? Right. So that's what we saw here when we were trying to decide, did 7 and 8 get compared? Well, we looked at the range, the numbers 7, 6, and 8. the first of those that was ever used as a pivot was 8, and therefore 7 and 8 get compared. Similarly, if I want to know, did 6 and 8 get compared, I would look at the range 6, 8 here. Which of those, well, in this case, there's nothing to say. Which of those, well, I guess there is. Which of those, or 6, 7, and 8, sorry, let's take a step back. If I wanted to know if 7 got compared to 8, then I would look at the set 7 and 8. One of those was picked as a pivot eventually. In this case, it was 8. And, well, that's the biggest one in the set, so it got compared to everything. More interesting maybe is to look at whether 6 and 8 got compared. Well, in this case they did, because out of 6, 7, and 8, the first one to get chosen as a pivot was 8. And so 8 was compared to 6, 7, and 8. So it was compared to 6 in particular. In fact, the only thing that could have stopped 6 and 8 from getting compared was if I had picked 7 as a pivot before looking at either of those two. All right. So this is what the picture looks like. I have this bunch of numbers. One of them is the first one to be chosen as a pivot. They're each equally likely, and there are 2 of them that will cause x and y to be compared. If I choose x as the first pivot, I'm going to compare x and y. If I choose y as the first pivot, I'm going to compare x and y. Otherwise, if I choose any of these things, I will never compare x and y. Okay. So, the probability that x, little x, and y are compared well, there's 2 outcomes where they're compared. And the sample space is all of this stuff. And how big is this set? Y minus x plus 1. So the probability that x and y are compared is 2 over y minus x plus 1. Let's see if that makes sense. Well, what if x and y are side by side, like 5 and 6? Without even looking at this thing, without even looking at the way the algorithm ran, I can tell you that 5 and 6 got compared. And that's because one of them was chosen as a pivot first, and there's nothing, and when that happened, they were still both in the same subproblem, because there's nothing that could have split them into 2 different sides of this thing. Okay? So let's see, 6 minus 5 plus 1 is 2, so the denominator is 2, and the numerator is 2, so with probability 1, 5 and 6 got compared. On the other hand, to know whether 6 and 8 got compared, that would have happened with probability 2/3, because there were 3 things in that range, and 2 of them forced the comparison, and 1 of them doesn't. And right, that is equal to the expected value of the indicator variable xy. So it's not always completely trivial to figure out this expected value, even though it's only one probability we need to figure out. But that's just because it's not always trivial to figure out a probability. Yeah.
Does the probability only work if you have every number in the range? Like,
no, instead of thinking of, this stand-in, we use integers here because it's convenient, okay? So if I didn't want to, if I had something other than these integers, just think of saying, okay, you replace every element with its rank. So its rank is 1 for the smallest element, 2 for the second smallest element, 3 for the third smallest element, 4 for the fourth smallest element, and so on. then that's what x and y really stands for in this case, right? So,
Like, when you said it was 2/3, it only works here because we have 6, 7, 8, but like when it's
only tells you the number of things in there when you have all those integers. So, but just imagine that these integers that we're assuming are in this input array, imagine that's just, replace those with the ranks of the elements that are actually there. So 1 for the smallest element, 2 for the second smallest element, 3 for the third smallest element. Because it'll do exactly the same comparisons. If I sorted those integers, the ranks, it would do exactly the same thing as if I was sorting the original things, right? Because 1 is smaller than 2 because the smallest element is smaller than the second smallest element. So that's the way to think of it. I just don't want to have to put ranks around every symbol that I have here. Okay, so now we're golden. Sum x equals 1, n minus 1. Sum y equals x plus 1 to n of 2 over y minus x plus 1. That looks difficult. So, typical thing we do when we see something like this is we write it out longhand and see really what it means. So, in particular, usually starting with the innermost thing. So, we still got the outer sum, x is running from 1 up to n minus 1. But what about this innermost thing? So y starts counting at x plus 1. So when y is x plus 1, what's the denominator here? Two. Right. So, you know, if x equals 5, y equals 6, then this is 6 minus 5 plus 1. And that's the first thing, right? If x equals 5, we start counting at 6 here. So the first term in there is 2 divided by 2. Next up, next time through, y is equal to x plus 2. So what's the denominator? It's just getting bigger by 1, right? Before it was 2, next time through it's going to be 3, time after that it's going to be 4, after that it's going to be 5. And the only thing we have to look out for is, okay, what is it on the last one? On the last one, it's going to be something like 2 divided by n, because y only counts up to x here, and so that'll be n minus x. And let me just make sure I don't make a mistake. Although in the next step it's not going to matter at all. N minus x plus 1. Okay, good. So that's what that thing is. All right, let's beat that up into something a bit simpler. I'm seeing 2 on top everywhere. So that looks like something we recognize, but all multiplied by 2. So let's bring that out front. So all of these are 1s. Now, does this look familiar at all? Yeah. What does it look like? I'm seeing most of a harmonic number in here, right? a half, plus a third, plus a quarter, plus and so on, up to some number here. In fact, what am I seeing here? This is almost the whole harmonic number, h sub n minus x plus 1, except there's one term missing, the first term, the 1. So that means this thing must be h sub n minus x plus 1 minus 1. Okay. All right. So this is 2, the sum, x equals 1 to n minus 1 of h sub n minus x plus 1 minus 1. Okay, let's be a little bit sloppy here because we'll get an answer that we like anyway. This minus x is annoying down here. So, but I know that x is at least 1 and is sometimes bigger. So whatever this thing is, it's not bigger than n, right? So that's less than or equal to 2 times the sum, x equals 1 to n minus 1 of h sub n minus 1. And now we're done, right? This sum isn't changing now, or this thing inside isn't changing with x anymore. So all we have to do is know how many terms we have. X is counting from 1 up to n minus 1. So that's 2n minus 1, h of n minus 1. And let's be lazy again. It doesn't really matter. That's less than or equal to 2n, h of n minus 1. So let's just not bother subtracting the 1 here. We'll only get something bigger. And h of n is this weird thing that I would like to see a simpler description of. So what can you tell me about h of n minus 1? Smaller than what? So h of n is smaller than 1 plus ln n. So h of n minus 1 is smaller than ln n. So this is less than or equal to 2n natural logarithm of n. So we'll write that down. The expected number of comparisons done by quicksort when sorting an array of n distinct values is at most, so not more than, and we have to include this because there's several spots where we use an inequality here. 2 times n natural logarithm of it. So remember the sort of the best case running time for quicksort was, we decided, was about n log base 2 of n. So this is n log base, actually something bigger than 2. So that's actually smaller than n log base 2 of n, but we've multiplied it by 2. So unlike insertion sort, quicksort on average runs very close to its best case running time. Any questions? Okay, so if you have questions of a non-technical nature, I will be at the CCSS Prof Night tonight at Mike's place. So come by and ask me things, but not about assignments or stuff. Ask me about life advice. That's it for today.